The birth of Doppler radar. Before Doppler radar, tornado detection relied mostly on eyewitness reports and spotters risking their lives under the storm. In the mid-20th century, meteorologists needed something more reliable. That's when radar, a wartime technology designed to detect enemy aircraft, found a new purpose in weather science. By sending out radio waves and measuring their reflections from raindrops, radar could reveal where storms were forming and how intense they were. But it had one big limitation. It couldn't show whether winds inside the storm were rotating. That's what Doppler radar changed forever. Named after the Doppler effect, this radar could measure not just where precipitation was, but also how it was moving. That meant meteorologists could finally see rotation inside thunderstorms, the earliest signs of a possible tornado. The science behind the Doppler effect. The Doppler effect is a simple but powerful principle. When a sound or wave source moves toward you, its frequency increases. When it moves away, the frequency decreases. Doppler radar works the same way, except it uses microwave radio waves instead of sound. The radar sends out a pulse of energy into the atmosphere. When that pulse hits rain, hail, or dust, part of it bounces back to the radar dish. If the particles are moving toward the radar, the returning signal's frequency is slightly higher. If they're moving away, it's lower. By measuring this change, meteorologists can calculate wind velocity within a storm. This allows them to spot dangerous rotation, even before a tornado touches the ground. How Doppler radar scans the sky. Modern Doppler radars, like the U.S. National Weather Service's WSR-88D network, don't just send a single beam into the air. They scan the atmosphere in a 360-degree rotation, slicing through storms at multiple elevation angles. Each full scan creates a detailed 3D picture of precipitation and motion. The radar measures two main things: reflectivity, which shows how much energy bounces back, revealing where rain, hail, or snow is; velocity, which shows how fast and in what direction particles are moving relative to the radar. Together, these two pieces of data form the foundation of modern tornado detection. When meteorologists see a couplet on a velocity map, one side showing air moving toward the radar and the other showing it moving away, it's a strong sign of rotation. That's what experts call a mesocyclone, the spinning core of a supercell storm that can spawn tornadoes. Spotting the signature of a tornado. When Doppler radar detects intense, tight rotation close to the ground, it's often the first sign a tornado is forming. On radar images, meteorologists look for something called a velocity couplet, where bright green and red pixels sit side by side. Green represents air moving toward the radar, red, air moving away. When those two colors touch, it means air is spinning, fast. In some cases, radars even capture a tornado debris signature, TDS. That's when debris lifted by the tornado, like leaves, branches, or building materials, reflects radar beams differently than rain. The radar identifies these objects as irregular shapes, confirming that a tornado is not just possible, but actively on the ground. This is what allows weather services to issue tornado warnings with much more confidence and lead time, often saving countless lives. Dual polarization, a major upgrade. In the early 2000s, Doppler radars received one of the biggest upgrades in history: dual polarization technology. Traditional radar sent out horizontal pulses. Dual pol radar, however, sends both horizontal and vertical waves, providing extra detail about the shape and size of objects in the air. This helps meteorologists distinguish between rain, hail, snow, or debris, something older radars couldn't do. During tornadoes, this feature is crucial. It can confirm if the radar is detecting irregularly shaped debris, proving that a tornado is actually causing damage. In short, dual polarization radar enabled unprecedented clarity in seeing inside storms. Real-time tornado tracking. When a strong storm develops, Doppler radar scans it every few minutes, constantly updating meteorologists with fresh data. The velocity maps reveal whether rotation is tightening, an indication that a tornado could form soon. Meteorologists use software that automatically identifies rotational signatures and tracks them as they move. Once a dangerous pattern appears, Forecasters issue tornado warnings through the emergency alert system. These warnings often provide people with 10 to 20 minutes of lead time, enough to take shelter and prepare. It's not perfect, but compared to the pre-radar days, it's a monumental leap forward. Limitations of Doppler radar. As advanced as Doppler radar is, it has its limits. First, radar beams travel in straight lines, but the Earth curves. That means the farther a storm is from the radar site, the higher the beam is above the ground. If a tornado forms close to the ground but far from the radar might miss it entirely. Trees, hills, and buildings can also block low-level scans, especially in rural or mountainous regions. Another issue is update time. Each radar scan takes several minutes. In fast-developing storms, that delay can mean the difference between spotting a forming tornado and reacting after it's already on the ground. Despite these challenges, new technologies are being developed to make radar faster, more detailed, and more responsive. Mobile Doppler radars and storm chasers. Some of the most valuable tornado data doesn't come from stationary radar towers, but from mobile Doppler units. Radars mounted on trucks used by storm chasers and research teams. These mobile radars can drive close to supercell storms, capturing high-resolution measurements of wind fields, debris, and vortex structure just a few miles from the tornado itself. One famous example is the Doppler on Wheels (DOW) program, which has chased and recorded hundreds of tornadoes since the 1990s. The data from these missions helped scientists understand how tornadoes strengthen, weaken, and interact with their environment. These mobile radars have even documented multiple vortex tornadoes, where smaller funnels rotate around a central core, something no stationary radar could see in such detail. How radar images save lives. Every colorful radar image you see on TV or weather apps is more than just a visual. It's the result of billions of calculations per second, data that meteorologists interpret in real time. When a tornado outbreak begins, Doppler radar becomes the eyes of the storm prediction team. It shows where rotation is forming, how fast it's moving, and which towns are in its path. This information allows emergency managers to activate sirens, schools to move students to safety, and residents to seek shelter. In major outbreaks, such as the 2011 Joplin, Missouri tornado, radar data played a crucial role in identifying the storm's strength and direction, information that guided rescue and relief operations in the aftermath. Tornado debris signatures, TDS. One of the most groundbreaking uses of dual-pol radar is detecting tornado debris signatures. When a tornado is strong enough to pick up trees, dirt, and buildings, those objects scatter radar waves differently from raindrops. On the radar display, this appears as a dark ball, often nicknamed the debris ball. Meteorologists cross-check that spot with the velocity couplet to confirm a tornado is on the ground. This technology has saved lives by confirming active tornadoes even when they're hidden by rain or darkness, what meteorologists call rain-wrapped tornadoes. Next-generation radar, phased array systems. The next frontier in tornado tracking is phased array radar. Instead of waiting for a dish to rotate physically, phased array radars use thousands of small antennas that can electronically steer beams, instantly scanning entire storms in seconds. This drastically improves update speed and detail. Meteorologists can see how rotation develops in near real time, reducing delays in issuing warnings. NASA and NOAA are already testing this technology, and if implemented nationwide, it could revolutionize how we detect and respond to severe weather.